Ciao Carlo, buongiorno. Scusi, no, poi sto fino a sabato, ma sono arrivato. Ok.
So good morning, everybody. Welcome to this third day of conference, second day of discussions. The first discussion of the day is about how the structure of space-time influences the quantum theory. And our first speaker is Fabio Sciarrino, that we are welcoming from the University of Rome, La Sapienza.
Thank you so much. So thank you so much. Good morning. It's a pleasure being here. So in this lightning talk, I will try to provide you a short overall perspective on which sort of experiment you can carry out on trying to validate causal structure and to discriminate between classical and quantum description. I will be obviously brief. Let me see if okay, it's fine. So let me try to very briefly introduce the framework. We are discussing about causal inference. We already had several discussions on this point yesterday. And the goal is to decide which causal models are compatible with the observed data. So we have observed data, we would like to understand what is the causal explanation, and in particular, the focus will be, we would like to discriminate whether our data are compatible or not with a classical causal structure explaining our experiment. That's the framework, and to adopt this framework, we will exploit directed acyclic graph. So let me very briefly introduce the framework that we already have seen again yesterday. We want to describe the causal structure which is underlying our experiment. Now we are discussing about classical causality framework, and we need the following ingredients. First of all, we need to introduce nodes, which are events defined in space and time, which are random variables, which acquires a precise value. First ingredient. Second ingredient, we have arrow, which describe causal connections between different variables. Third, we have the arrow as a direction, which tells us that we have a causal influence from this variable to this other one. Then you can have general causal structure, for instance, this one, where you have some variable which is influenced by other variables, and then you can obtain a Markov condition that will describe how all these random variables are interconnected. Finally, you cannot have acyclicity because each node represents an event, so you cannot self-influence you influencing other events later on. And then what we have is that causal structure imposes constraints among the variables. We have this simple scenario here. X1 is influencing X2, X2 is influencing X3. That's a very well-defined framework, and now we would like to exploit it to carry out tests on quantum mechanics. First, let's start from the Bell test, the typical scenario. How can we see the Bell test using a DAG framework? When we have a Bell test, we have a bipartite scenario. We have two parties, Alice and Bob. These A and B are so accessible variables. This should be a B. Then you have the measurement inputs, which are two other random variables, X and Y. X is influencing only A, epsilon is influencing only B. And then finally, we have a latent variables, lambda, here. And then this DAG is describing a Bell test. Up to now, I'm assuming causal connections in the classical framework. And if the following DAG is valid, you get some local causality constraints that will lead you to some inequalities, which at the end are the Bell inequalities. And then what you can do, you can elaborate this local causality constraint, you will get this inequality, you get a bound. And then if you perform a test and you violate this bound, you can conclude that your data are incompatible with this causal structure. And so that's the interesting part, how you can exploit this DAG and this causal structure to discriminate between quantum and classical models. You have statistical data that you perform on your experiment, and if you now violate the causal constraint, you can exclude that your data are compatible with the causal structure that you have assumed. Why is this interesting? Because this can be exploited to demonstrate the non-classicality of physical systems. So again, how you conclude the non-classicality of a physical systems, you have two ingredients, the statistical data that you acquire from the experiment and the causal structure that you assumed to be the one which properly describes what you are carrying out in the lab. So now this was a first starting point. If we see nowadays experimental effort in quantum causality, I will identify two mainstreams. One on indefinite causal structure. This was already discussed by Fabio on Monday. I will not focus on that. I will focus on the second scenario, which is non-classicality in a causal framework, which, as I said, exploits this DAG formalism to describe what you are observing in the lab. So now I've shown you the Bell test, and one may wonder, is a Bell test the simplest causal structure where you see a departure between classical and quantum predictions? So what can be the simplest causal structure scenario? The following one, where you have A and B which have some correlations, and this correlation may arise as a direct influence of A into B, also to the fact that A and B have a common cause, which is lambda. But now, if you take these two scenarios, there is no experimental test that can discriminate whether you have this causal structure explanation or this other one. So let's move to a slightly more complex scenario, which is an instrumental scenario, which was introduced by John Pearl, which was analyzed by John Pearl in the classical framework 2 years ago. And this is the instrumental test scenario. You have two variables, A and B. You have variables X that influence A. And now you wonder whether A and B may be influenced by a variable lambda, which can create a correlation between these two variables. So you see, you have now another DAG, another causal structure. And then now the question is, if one analyzes this causal structure, can we observe a departure between quantum prediction and classical prediction? So what you need to do, you need to take this causal structure here. You need to derive a classical Markov condition. In this case, one assumes A and B to be dichotomic variables, which can take value 0 and 1. And you can take the variable X that can be trichotomic, which can take the value 0, 1, and 2. You now have this causal structure, you derive the constraint, and you find these inequalities that must be fulfilled by any data which is coherent, is compatible with such a structure. This is what you obtain with a classical model. Now you can go to the lab and you can ask yourself, if I have some kind of quantum correlation, can I violate this bound? And the answer is yes. So obviously, if you have, in this case, quantum correlation arises because lambda, instead of being The classical variables could be, for instance, an entangled state. So what you see, the philosophy of this slide is that you change causal structure, you derive a different classical bound, and you can always ask yourself, does quantum resources allows you to violate this bound? Let me now add another ingredient that we can exploit experimentally when we work in this framework, is the concept of interventions. So when you carry out an intervention, what you do is that you force variables in your structure to assume a precise value. And these interventions break all the incoming causal arrows. For instance, you can take this instrumental scenario, you can do an intervention on the variable A, you fix the value of the variable A, and this will remove all the arrows that were influencing A because you forced A to take some value. And when you exploit intervention experimentally, this allows you also to identify some resources that otherwise you could not see directly. So my talk was wanted to bring a connection with the experimental perspective. So I would like to show you how you can take this framework here, which is the simplest one, and how you can move this paradigm in the lab. So this is a apparatus which implements this causal structure and which allows you to violate the bound I've shown you before. So in this case, first ingredient, we have a source of entangled photon pairs. Here, this source creates two photons which are entangled, and this will be our quantum resource that will be here instead of the local eigenvariable model. Then you have Alice and Bob on the two sides. Alice and Bob will perform some measurement, and the measurement will be the variables A and B. And in this, let me go back. In this scenario, you have only one random variable. That's the difference with the Bell test. In the Bell test, Alice and Bob both decide what to measure. In this scenario, only Alice, you have only a variable X, which is influencing A, and then A is directly influencing B. How do you perform this in the lab? This is Alice. You measure the photons on the Alice side. You send the output, the classical information, to Bob, and Bob here has a very fast device which, depending on the results received from the variable A, is changing which kind of measurement Bob is performing. So you see, we have an ingredient here. We implement this direct arrow via this classical information. We need to have some fiber loops to delay the photons manipulation. These are more technicalities. But you see at the end how you implement in the lab this direct arrow which connects A and B. So at the end, what you have, this is your apparatus. Again, X is decided here by a quantum random number generator. Here, that's X variable, that's the A variable, that's the B variable, and this is a lambda. What you can do something more. Again, to show you another ingredient, you can do an intervention in the lab. And how you do the intervention is shown here. What you do, you fix the output of the measurement. So you don't measure the photon, you decide what is the output, and this is how you perform the intervention. So by having this classical information that we impose to the apparatus here, we are inserting this intervention on the A, and this is now influencing all the experiments. What was the goal of this perspective was to show you how really you can come in the game. You can generate state, you can perform measurement, you can have direct arrow, and you can force some variables. I have 1 minute left, so I would like to show you another perspective in this last minute, where I've commented you about the Bell scenario, which is the following one, where you have a DAG. But now the principle is that you can take this DAG formalism and extend it to much more complex networks. For instance, you have a triangle network here, or here other kind of networks. And what is the interesting part is that by this DAG formalism, you can extend your approach to any, I would say, arbitrary configuration. You can derive some bound, and you can see whether quantum resources allows you to violate this bound in the different scenario. What I would like to show you to conclude on what is coming out now recently, there is a strong interest in the triangle network, which is the following one. You have many results in this triangle network in the last, I would say, couple of years, because it seems that these triangle networks have some very peculiar quantum correlation which are arising. And when you implement this triangle scenario, you may implement it in the following way. You have Alice, Bob, and Charlie. You have some measurement setting for the tree. Or someone also proposed to have a triangle network where the measurement settings are decided by the measurement itself. So you see, it's a closed triangle without any external variables. So this concludes my lightning talk. The goal was to provide you an overview on these theoretical tools, but also to show you how you can bring this approach into the lab. And you may have two opposite directions to find out the simplest structure, this instrumental, or the opposite one, to find out complex structure, which allows you to somehow maximize the departure between quantum and classical. Thank you for your attention.
Thank you, Fabio.
Okay, yeah.
Thank you, Fabio, again. I welcome the next igniter of discussion, Alex Smith from St. Anselm College. Please.
Thank you very much. So thank you for the organizers for putting on such a wonderful conference. It's been great seeing people and having discussions again. So what I thought I would do in trying to ignite discussions with this question is I just wanted to start off with the postulates of quantum theory and try and argue why what we know about space-time, how it might affect each one of these postulates. So we have states live in a Hilbert space, we have the Born rule, we have the collapse of the wave function or the state update rule, we have the Schrodinger equation, and then we have a way in which we can combine systems through the tensor product. And what I want to try and argue is that we really need to rethink every one of these postulates. So, and I don't want to just do this sort of willy-nilly. I want to look to one of my favorite physicists, John Wheeler, who advocated a radically conservative approach to physics. He said, let's insist on adhering to well-established physical laws. We should be conservative, but follow those laws into their most extreme domains. We should be radical, where unexpected insights into nature might be found. So this is exactly quantum gravity. And by conservative, I want to mean our best theory of space-time, general relativity. So what general relativity tells us how we might have to rethink some of those postulates. So I think maybe it's uncontroversial in this audience to say that quantum gravity requires a new dynamical paradigm. All of our current quantum theories, they make use of some classical background structure in their construction. So in non-relativistic quantum mechanics, we have background classical parameter time. In quantum field theory, right, we impose canonical commutation relations on equal time hypersurfaces, or maybe we have a time-like killing field where we can define a nice vacuum state. But when we go to quantum gravity, what we're trying to do is simultaneously quantize both matter and space-time on equal footing, right? So we can't use any of that background classical structure. So the first thing I want to think about is how our dynamics might have to change. So usually if we want to describe the dynamics of a ball, right, I give you some initial conditions, and then you write down F equals ma, and you propagate these initial conditions forward in time. But another way to think about the dynamics, and I'm borrowing some language from Carlo here, is that really what dynamics is about correlations between partial observables. So I can tell you everything about the dynamics of this ball by just telling you about correlations between what I'll call a partial observable, namely the height of the ball, some other partial observable on the clock. I'm not sure why okay, this could get messy. So what we need to do is construct complete relational observables. I'm not sure why the slides are not, okay, this is going to be, there's something wrong with the slides that they're not all loading. Is it the arrows? No, but like there's stuff that should be showing up here and here. Okay, well, it's going to be a little hard with incomplete equations here, but What I want to argue here is that we should really be looking at complete relational observables, namely something that encodes the system when the clock reads a particular time t. Okay? So how might we do that in a quantum theory? Well, we might start off with a Hamiltonian constraint, right, where we demand that our physical states of our theory are annihilated by our constraint operator. And here I have a very simple one, just the Hamiltonian of a clock plus the Hamiltonian of a system. And yeah, so there's an error here. Like, can I just get my computer? Is that possible? It's going to be really... Sorry? Oh, I mean, I feel sorry for the audience. Like, with half the slide, like, there's... Is it okay? Yeah.
You have a connector?
I have one too. No, it's okay. Oh, thanks. With the usual Born rule. We can write this as an expectation value of those complete relational observables. This is actually a Dirac observable. It's going to commute with the constraint. And then what I found really interesting was that you can also define this conditional state of the system by basically taking your physical state and projecting it onto one in which the clock reads the time t, right? And this is the idea of Page and Wooters. And what that allows you to do is that you can write this conditional probability in a much more familiar way, just with the standard Born rule, right? Taking the amplitude squared with A and the state at the time t. And moreover, this conditional state here satisfies the Schrodinger equation. So this is really exciting for me in the sense that just from the Born rule, you can recover a relational notion of dynamics, namely unitary dynamics. So you don't have to postulate that a priori in some sense. I'm trying to be controversial. So why might you want to do this? I think Bill Wooters gives a very nice reason in his one of his early papers. He says, one motivation for considering such a condensation of history is the desire for economy as regards to the number of basic elements of the theory. Quantum correlations are an integral part of quantum theory already, so one is not adding a new element to the theory, and yet an old element time is being eliminated, becoming a secondary and even approximate concept. So, okay, so we should be thinking about complete relational Dirac observables. We should be using the Born rule in this way, and maybe we don't necessarily need to postulate unitary dynamics a priori. We don't have to talk about necessarily the collapse of the wave function or the state update rule. The usual way we would think about making sequential measurements is we have some system of state here, and at some time t1 we would make a measurement and the state gets updated. Then we have some unitary dynamics, and then the state gets updated again. But what you could do is just ask, well, what's this two-time conditional probability? What's the probability of B when the clock reads T2, conditioned on A when the clock reads T1? And again, just using the standard Born rule and expressions for conditional probabilities, you can recover the correct propagator. again. So you don't actually have to talk about this big physical state actually collapsing anywhere. The next couple slides I want to talk about is how, depending on our choice of clock, how our notion of dynamics might change. So one thing you might expect is that your clock and system could interact. And indeed, if we think of a gravitational theory, we can't ever shield the gravitational interaction. So there should be some interaction between our clock and our system. Right? And if you go through the same sort of analysis, you get out what we call this time non-local modified Schrodinger equation. So these first two terms are what you would expect the usual Schrodinger equation. But now if you have an interaction, you get this time non-local integral operator here, where the kernel of which depends on exactly the details of the interaction. So again, you're getting a modification to the usual notion of dynamics. Another possible modification, this is from Gambini, Porto, and Pullen, is that, well, maybe you don't want to define your dynamics relative to this little t here, because that's a partial observable, might not be gauge invariant, might not commute with the constraints. So what you should really do is introduce another Dirac observable and ask, what are the conditional probabilities of this observable here, given that this clock observable reads a particular time t. And so they go through and they construct another expression, a different expression for these conditional probabilities. I don't have time to unpack it. But when you do that, what it allows you to do is to take into account fluctuations of the clock. And what happens in that case is that you get a fundamental decoherence mechanism that emerges that actually depends on the fluctuations of the clock. So here, this is a Lindblad equation. This is the usual unitary part. And then here would be some decoherence that results from the fluctuations of the clock. Another possible modification to the dynamics that might result is if you consider that there's a fundamental period of time. So this is some work by Wendell, Martinez, and Boyewald, where they considered that, okay, instead of having this big monolithic time variable that runs from minus infinity to plus infinity, you have some oscillating clock. And what they looked at was that, okay, if we have this oscillating clock and then we have some system, they considered a harmonic oscillator, right? And then they unwound this time, and you can look at the evolution of this oscillator relative to this clock. And if it starts off in a coherent state, it starts to oscillate back and forth, just like you'd expect, right? But over time, it starts to get scrambled, and these oscillators become out of sync. And again, you get a modification to the dynamics on the choice of clock. Another nice idea in this direction is by Guillain and Mendes-Vidal. And this was a nice essay in this year's Gravitational Research Foundation Awards, where they considered an FLRW space-time, right, where they had a scalar field and a cosmological constant. And now you have a choice of what clock variable you want to use, and depending on what choice of clock variable, they found that you get different physics. So here, what I'm plotting is the evolution of the volume of the universe. Not I'm plotting, these folks are plotting, is the evolution of the volume of the universe as a function of the time variable canonically conjugate to the cosmological constant. And what you see is when comparing to the classical solutions, you can actually resolve the singularity. And then if you were to actually look at the clock variable taken as the scalar field, you can actually get a recollapse. So the volume doesn't go out to infinity, but you actually get a recollapse relative to this clock. So you get different physics depending on which clock you're looking at. Finally, the last thing I want to talk about is this last postulate and the notion of subsystems, right? So let's suppose that we have just a classical three systems, and we want to describe the total phase space. Well, what we would do is we would take the phase space of each one of these systems and take the direct product, and that would formulate our total phase space. And then if we wanted to quantize that, we'd put hats on everything, and we would get what we would call our kinematical Hilbert space, where this is just the Hilbert spaces associated with each one of these phase spaces, and we take the tensor product of them together. But then Hal was pointing out is that in his talk on Monday, when we have constraints, right, this notion of tensor product might not survive. That is, we would demand that our physical states are those that are annihilated by our constraint operator, and this tensor product structure may not necessarily survive. Right? You can think of it as if you have two qubits, and so your Hilbert space would be C4, this is C2, tensor C2. But then if you were to restrict the antisymmetric subspace now, right, then the Hilbert space is only C3, and you lose that tensor product structure. Right? So the question is really, how can we recover a physical notion of subsystems on this physical Hilbert space? And so this is some work I've done with Shadi Ali Ahmad, Thomas Galley, Philip Hoon, Max Locke. So the idea was that, well, what we should be really doing is constructing these relational Dirac observables and we can look at commuting subalgebras of them. So if we have our three systems, we can construct relational Dirac observables of system B relative to A and system C relative to A. And if we show that they commute, and following some of these references here, you can actually get a physical notion of subsystems, and such that you can write your physical Hilbert space as this tensor product here. So these commuting subalgebras can induce this notion of subsystems. Okay, so that's it. That's everything I wanted to say. So, namely, coming back to these postulates, that we should really think of states not at an instant of time, but states that are encoding correlations between a clock and a system. That are observables, we should really be looking at these complete relational observables that encode information about what the system is doing when our clock is reading a particular time t. That the Born rule should really be about these relational observables. And then from the Born rule, we can get out a notion of dynamics. We don't have to necessarily talk about the state update rule. I gave a number of different ways in which our dynamics can depend on our choice of clock, and that this notion of tensor product structure might have to get updated when we have constraints. So with that, I'll end there. Thank you.
Thank you so much, Alex. Also, thank you for keeping the right time despite the technical difficulties.
Sorry about that, yeah.
No, we have brilliantly solved it. I can give it to you. No. Okay, better. Is it working? Microphone. Is the microphone okay? It's okay now? Yeah. Right. So, Doreen, Fraser, from Waterloo.
Thank you. Thank you. So what I'm going to do is I'm going to talk about quantum field theory from a philosophical perspective and a slightly historical perspective, since I'm a philosopher and historian. I'm also going to sort of go out on a limb and talk about work in progress that has to do with measurement in quantum field theory, because this is a conference related to information theory, and I think there's going to be some interest in that particular topic. All right. So as a starting point, answering this question, how does the structure of space-time impact quantum physics? I'm going to start by comparing the theories by themselves, insofar as it's possible to do that in any quantum theory. Of course, the next slide is going to be about measurement, but for the moment, I'm just going to try to stick to the theories by themselves. And so to answer this question, I'm going to be contrasting non-relativistic quantum mechanics with relativistic quantum field theory. And so I want to stress that I'm not talking about gravity at all in this talk, but I am going to try to say some things that would at least extend to more general space-time, are not just restricted to Minkowski space-time. So would include globally hyperbolic space-times. So the point of contrast here is that, as we know, relativistic quantum field theory is a field theory. There are an infinite number of degrees of freedom. And if we take that seriously, which the physics sort of forced us to do back in the history of developing the theory, then there are some implications for how we represent quantum physics that come from that starting point. As a philosopher, I'm also interested in the issues related to how scientific theorizing as an enterprise produces knowledge. So one of the things that's interesting here is the more familiar non-relativistic quantum mechanics case. The questions about whether there were physically inequivalent quantum theories that arose at the very beginning with Heisenberg's and Schrodinger's formulations got solved very quickly by demonstrations that they really were physically equivalent representations, physically equivalent theories. So in contrast, for reasons directly related to the fact you have an infinite number of degrees of freedom, that doesn't happen in quantum field theory, right? So there's going to be unitarily inequivalent Hilbert space representations that are physically relevant for representing quantum fields, and there's all sorts of implications that arise from that. So the epistemically interesting point is you have a bunch of different ways of formulating quantum field theories. In contrast, if you think about the reconstruction program we've been hearing about, the goal there is to come up with alternative mathematical formulations of non-relativistic quantum mechanics, but there's a kind of a fixed endpoint there, right? The goal is usually to recover something like the von Neumann postulates for non-relativistic quantum mechanics. In contrast, there's a bunch of different mathematical formulations of quantum field theory on the table. All right, so I've included here on this slide a bunch of implications and differences between relativistic quantum field theory, just the theory, and non-relativistic quantum mechanics. Particles are not fundamental. There's a bunch of converging arguments that lead to that conclusion. And I also wanted to point out that there's implications for the dynamics as well as for the kinematics. In particular, it becomes non-trivial to give unitary representations to dynamics in this context where you have unitarily inequivalent Hilbert space representations. Okay, so let's now think about the theories and how measurement comes into the picture. So this slide is the conceptual frame slide. This is a work that I've been doing in collaboration with a PhD candidate at the University of Waterloo in applied math, and also at the University of Patras, Maria Papageorgiou. Can you yes. And Maria has a poster with more information about what I'm going to be talking about back in the poster session. All right, so well, first of all, what are the motivations for thinking about measurement theory for relativistic quantum field theory? Well, some of the motivations, I take it from thinking about these kinds of questions, come from the field of relativistic quantum information, where you have an interest in doing information-theoretic tasks with local systems, and you want to make sure that you're being very careful to include fully relativistic representations in so far as possible of the systems and the measurement processes that you are that you're operating with on these systems. So what I have in mind here by measurement theory is the measurement theory for local measurements, in analogy to what we would find in ordinary quantum mechanics, and not, for example, asymptotic scattering measurement scenarios, which we're much more familiar with from particle physics. There's another source of motivation for recently. There's been a lot of work on this type of topic about measurement in quantum field theory, and that's been spurred by an old paper of Raphael Sorkin's, which many of you may be familiar with, about impossible measurement scenarios in relativistic quantum field theory. And essentially, the idea is you can show that if you just naively take measurement theory from non-relativistic quantum mechanics, apply it to relativistic systems, then there are scenarios in which you can end up with superluminal signaling. So then this is another motivation for thinking about these types of issues, and there's been a bunch of recent work, flurry papers, on that particular kind of scenario as well. All right, so here's the conceptual frame for how I'm thinking about this topic. So on the left-hand side, we have the somewhat artificial distinction between non-relativistic quantum mechanics by itself and the measurement theory that goes with it. So this starts with von Neumann. There's lots of developments all the way through. What I'm thinking of to fix concrete reference is the book called Quantum Measurement by Bush and collaborators, and there's a bunch of other really nice papers and authoritative articles on this by Bush. So then the question that I'm posing is, we have various versions of relativistic quantum field theory, bracket that complication for the moment. What is the analog of quantum measurement theory for non-relativistic quantum mechanics that fits with relativistic quantum field theory? So that is, if we're doing local measurements on quantum fields, what is the measurement theory like for that scenario? Okay, and then there's the footnotes, which is part of the conceptual frame. So I take it that the measurement problem, so the point here is I'm not talking about the measurement problem, I'm talking about a sort of mathematical step that happens before the measurement problem arises. So this is my seed for the discussion. Anytime you say, I'm mentioning the measurement problem, but I'm not talking about it, that's a good way to generate discussion. But here's what I mean by that. I mean that initially, the measurement problem is this whole cluster of issues, but the initial inspiration for it in non-relativistic quantum mechanics was thinking about conditions under which you apply measurement state update rules versus, say, the Schrodinger dynamics state update. And then I think what I want to talk about for quantum field theory is that prior step of the mathematical articulation of the measurement theory that goes with quantum field theory. So there's two question marks at the bottom on the left, and so then the measurement problem, cluster of measurement problems, will be whatever results on the quantum field theory side after we've done this articulation step. All right, so I'm going to leave you with, as I say, this is work in progress. Maria and I are finishing a paper on this that will hopefully be finished soon. There are different approaches to this problem of how to formulate a measurement theory for quantum field theory. And here are two approaches with quite different philosophies. I don't want to minimize the differences between these approaches, but I think what's interesting from my sort of philosophical interpretive perspective is they start with different approaches and end up with two conclusions which are interesting in common between the two approaches. Okay, so what are the two different approaches? The first approach is the approach that's known as this detector models approach. And I've learned a lot about it from the relativistic quantum information group at the University of Waterloo. There's also a poster related to this at the back that you can check out if you're interested in learning more. But the basic idea here is you start with concrete models of realistic detectors, such as Unruh-DeWitt type detectors, and then you use non-relativistic quantum mechanics to model the detector, and you avail yourself of the projection operators you get from standard measurement theory with respect to the detectors. But then you model the system that you're measuring using quantum field theory. And because you're coupling a non-relativistic quantum system to a relativistic field theory, you have to be very careful about how you do the coupling. So a lot of the hard work comes in figuring out how to do the coupling and how to represent things in such a way that you're going to be violating relativity, but minimize violations of relativity when you're setting things up this way. So that's the first kind of pragmatic approach. The second approach is more of a principled, kind of high-level approach within the algebraic framework for quantum field theory, which has been recently proposed by Fraser and Doreen. And so the idea here is that everything gets modeled using algebraic quantum field theory. By everything, I mean you, of course, model your system that you're measuring using algebraic quantum field theory, but you also couple it to a probe that you also represent using algebraic quantum field theory. And then the measurement theory is how you make sense of a measurement that the probe does of your algebraic quantum field. Okay, so here are the two common conclusions, which I think share some themes with the talk we just heard, and I presume we're going to share some themes with the talk we are about to hear about the implications of space-time structure for quantum theory. So the first is a point about localization. And the point is that often local field observables that are associated with space-time regions, either directly as in algebraic quantum field theory or by smearing, are interpreted as, those algebras are interpreted as representing operations that it's possible to perform in that local region. Once you introduce the probe, this picture is no longer the picture to have of the target system field operators that you're representing. So there is, of course, localization to regions represented within the frameworks, but it happens in a different way than we're used to. Second common conclusion is about the state update rules. So of course, part of doing a new measurement theory is coming up with new appropriate state update rules. When you look at these state update rules in both of these frameworks, the selective state update rules that you get can no longer be interpreted as representing physical changes of state that happen in some region of space-time. Now, the routes to getting to these conclusions are different. The relativistic ingredients and quantum field theory ingredients are very similar, but the conclusions are the same. So if we think back to Nick's talk about what Aristotle said we should think about criteria for what it is to be, so I'll end on a philosophical note. The criteria was to be is to be somewhere, right? So what the implication of this is to be is to be somewhere, then these physical collapses are not, changes of state are not happening anywhere, so they're not being. Another way of putting that is that the selective state update rules perform the sort of essential function of giving you conditional probabilities, but this is a version of an epistemic interpretation of the state update rule, which is not being argued for as an interpretive choice, but is coming out of the reformulation of the state update rules in this version of measurement theory. All right, so I will leave it there.
Thank you, Doreen. I have to apologize for my clumsy presentation before, but you were on the stage from the beginning. You needed no presentations. Yeah, thank you so much for the very inspiring presentation. And our next igniter of discussion is our own Emily Adlam from here, Western University and the Rotman Institute.
Now it's working? Yes, great. Okay. Yeah, so in case you haven't heard enough of it yet, I am going to talk again about the arrow of time, but I hope it will shortly become evident why I am talking about it today rather than yesterday, and it is not purely because the arrow of time prevents me from going back and changing the past. So speaking of which, why exactly can't I change the past? Or more precisely, why do all of us have the general impression that we are able to produce changes in the future and not in the past? So there's kind of a standard account of this in philosophy, which says that the inaccessibility of the past is down to thermodynamics. So roughly speaking, the idea is that the kinds of small local changes that we can make in the present do in fact produce changes in both the future and the past, but because of the thermodynamic gradient, the changes are much bigger and more diverse in the future, so we just kind of notice those ones more. This also covers accounts which say that the causal asymmetry supervenes in some way on the memory asymmetry, because most people think the memory asymmetry also comes from thermodynamics. So there's something a bit weird about this account, because the thermodynamic gradient we now understand is statistical. It comes from averaging over the behavior of a large number of particles. And that would seem to mean that if the inaccessibility of the past is indeed a consequence of thermodynamics, it should follow that if I try a very large number of times, I will eventually succeed in changing the past, in the sense that I will eventually make a big change, a big substantive change of the kind that we typically think we are able to make in the future. And that seems odd because, to me at least, the inaccessibility of the past does not seem in any sense approximate. It's a really rigid, unforgiving barrier. Furthermore, if I could change the past, one would think that if I tried enough times, I would succeed in making a composition like this. So here, my past self, Emily 1, takes a bit and sends the value of that bit to my future self, Emily 2. Emily 2 flips the value of that bit and then sends it back to my past self, Emily 1, who receives it just in time to use it as the content of her original message. So the value of that bit now has two different values at once. So it seems that if I succeed in producing this kind of composition, I've created a contradiction. And assuming we're not allowing exotic things like branching universes, that just can't occur. Moreover, it can't occur even once. The universe can't contain even one contradiction, which suggests to me that the reason I can't do this kind of composition can't be a purely statistical fact. There has to be some absolute prohibition written into the laws of nature that prevents me from doing this kind of thing. So I can see roughly two ways of achieving this. The first would be for the laws of nature to interfere with my free will in such a way that even though I'm a troublemaker and I would definitely make this composition if I could, nonetheless every time I set out to do so, I mysteriously find myself changing my mind. The alternative is that the laws should restrict the set of processes available to me such that although I have local free will to compose things in any way I like, I don't have the processes available to me which could be used to create this kind of contradiction. So focusing on that latter option, that leads to a natural question. What is the most general set of processes which the laws of nature could allow, which are compatible with agents locally having free will, but which nonetheless don't allow us to produce contradictions? And that, I take it, is exactly what is studied in the process matrix framework, which Flaminia told us about on Monday. So the idea there is precisely to define the process matrix in such a way that agents can locally do what they like inside their labs, but nonetheless, nobody can ever produce the kind of contradiction that I just showed you. So there are both classical and quantum versions of this, and the classical version says that the composition I showed you on the previous slide is not allowed because the identity matrix around a closed loop, like on that previous slide, is not a valid classical process function. So if the laws of nature only allow valid process functions and process matrices, that kind of composition just can't happen. So to me, this seems like a really interesting example of a very new piece of research in physics, a new research program, offering us a new way of thinking about what is a really old philosophical problem. So far as we can tell, all known processes seem to be causal. That is, all the processes we know that we can implement in the real world. So the definition of causal I've shown up here, but I won't have time for details, so I hope people who work on this framework will forgive me for speaking in a slightly imprecise way. Very roughly speaking, a causal process is one where we can assign a strict partial order to the experiments taking place in the process, such that the outcomes of later experiments depend only on the inputs to earlier experiments. And what I want to emphasize about this definition is that although we typically think of causes as being asymmetric, there's nothing really asymmetric about this definition. I can always reverse my process by renaming all the inputs as outputs and changing all the arrows in all the arrow directions in my strict partial order, and the result will be a process which still obeys the causality condition. So there's the direction is not really important here. What's important in this definition is that there's a well-defined order which never loops back on itself, such that these processes can't be used to create contradictions like the one I showed. So I think it's an interesting question as to why we don't see any of the non-causal process matrices in nature, or perhaps we do and we just haven't found them yet. I have some thoughts about that, perhaps we can discuss later. But for now, let's just assume that the way in which the laws prevent inconsistencies and contradictions is by requiring that all possible processes are causal. Now that obviously has consequences for the way in which processes can be composed with one another. In particular, the output of one signaling process can only be used as the input to another signaling process if that second process produces an output which is further along in the strict partial order. So all the processes end up having to be oriented in a consistent way in this kind of flow through the causal order. Moreover, that also has consequences for agency, because we can think of an agent making a decision as being like a process, right? Agents take as input a set of memories and sense data, and they produce a decision, and that decision can then be used as inputs to other processes. So if all allowed processes are causal, agents will find that the outputs to their decision-making processes can only be used as the input to other processes if those processes are oriented in the same way relative to the strict partial order. So if we think of the strict partial order as representing something like the future and the past, it follows that agents embedded in this big process graph will find that they can only use their agents as inputs into processes which are oriented towards the future, and therefore agents will indeed find that they can only change the future and not the past. What I really want to emphasize is that nothing in this account requires any kind of fundamental time asymmetry. As I said, we can always reverse the direction of a causal process and it will still obey causality. So the direction here is not built into the process. It comes from the fact that the agent has a perspective, and the perspective of the agent imbues this graph with a perspectival asymmetry. We think of our decision-making processes as being oriented from the past towards the future, and then we find that because of the way we're embedded in the graph, we can only use those decisions as inputs to other processes oriented towards the future as well. It's a bit like a road. Obviously, you can hop on a road in any direction that you like, but once you're on it, you have to keep going in the same direction. So from your point of view, there's a really strong asymmetry. You can only travel in one direction along the road, but that asymmetry is not down to any asymmetry in the road itself. It's purely a consequence of your perspective as a person traveling along the road in a certain direction. And this kind of causal flow is the same. We don't need an underlying asymmetry to explain why we can only change the future. It's just because we happen to be traveling along the process graph in a certain direction. So what I conclude from this is that we don't need to appeal to thermodynamics to explain why the past is inaccessible. There's nothing statistical about it. Certainly thermodynamics is part of the story, because thermodynamics probably does a lot to explain why there exist complex systems like our brains. So thermodynamics probably has something to do with the production of our perspective. But once that perspective exists, the inaccessibility of the past relative to the direction of that perspective is an absolute fact that's written into the laws of nature. It doesn't need to be attributed to statistics or thermodynamics. So I think this is really interesting, because basically we started out without assuming anything about space-time, temporal order, or anything like that. And essentially, just by imposing a consistency condition, we got quite far towards deriving the structure of space-time, because the strict partial order that we get with causal processes is very similar to the causal structure of space-time, which of course can be expressed as a strict partial order on space-time points. So that there's a proviso there that we perhaps still need a better explanation of why we don't see the non-causal processes, or at least we don't see them very much. But nonetheless, it seems to me that the process matrix framework is offering us a really interesting possibility to start explaining the structure of space-time, explain why it is the way it is, purely as a consequence of these kinds of consistency conditions. And I also find myself wondering if maybe we could do more. If we think a bit harder about consistency conditions, could we do something like explain the dimensionality of space-time, explain why matter has to curve space-time? You know, how much of this follows from the need to have consistent compositions of processes? So I think that possibly some approaches to quantum gravity are maybe missing an opportunity here, because many approaches kind of just assume global hyperbolicity, and therefore they rule out these kind of loops by fiat. But if we don't rule out these things by fiat, and instead we think seriously about the kinds of consistency conditions that are required, perhaps that could lead us somewhere really interesting. So I'm very keen to hear what you all have to say, so perhaps I should stop speaking and we can move towards discussion.
Thank you, Emily. Thank you so much. So it's time to take a break, and we will start a discussion in 30 minutes.